Today we're going to review what we've learned so far in our Forces in Motion unit. We've done lots of activities in class. We've had many concept checks, and some of you haven't redone the concept checks. And I want to make sure you understood all those concepts. So if you want to go back and correct those, you can to get a better grade. All right, first, what is speed? It's one of the very first things we talked about in this unit. So if someone were to ask you to describe speed, could you? In class, I've told you a way to help you remember how to calculate speed. Remember this video?
Hello. Remember how fast you ran that race? You didn't skip a beat, you quickly increased the pace. You traveled more ground in much less time. You accelerated more each second to the finish line. Well, runner, you know speed is distance over time. Meters per second's an example so fine. Velocity small cause there's direction implied. It's all about the way you move now. But when you slow down and didn't gain much ground, every second you ran, you decelerated, then you set your mind to win that race. Accelerate the pace, almost like you would be in chase. Well, runner, you know speed is distance over time. Meters per second's an example so fine. Velocity small cause there's direction implied. It's all about the way you move now. Remember how fast you ran that race? You didn't skip a beat, you quickly increased the pace. You traveled more ground in much less time. You accelerated more each second to the finish line. Well, runner, you know speed is distance over time. Meters per second's an example so fine. Velocity small cause there's direction implied. It's all about the way you move now. Speed is distance over time. Meters per second's an example so fine. Velocity small cause there's direction implied. Speed is distance over time.
Okay, so a way to describe motion is speed. All right, an average speed is the rate of motion calculated by dividing the total distance traveled by the amount of time it takes to travel that distance. Constant speed means that speed never changes. It's at a constant level. And of course, instantaneous speed is speed at any given second. So, everyone should know the formula used to calculate speed now, correct? Speed is distance divided by time. Okay, now let's do some practice problems. A football field is about 100 meters long. If it takes a person 20 seconds to run its length, how fast was the football player running? Now, the first thing you need to do is that it tells you how fast was the football player running. That is a speed. So it's asking for speed. We know speed is distance divided by time. The distance is 100 meters. The time is 20 seconds. So the math should be pretty simple. 100 meters divided by 20 seconds is 5 meters per second. Again, remember to always use the units. If you just put a number, that is not a measurement like speed would be. A measurement like speed would always have a unit and a value. Alrighty, so now that you know the formula, you can change it around. Like if you know the speed and you know the time, you can calculate the distance. If you know the speed and you know the distance, you can calculate time. So let's do a couple more practice problems. All right, what is the speed of an airplane that can travel 2,500 meters in 10 seconds? Okay, first, what is the problem asking for? Speed. So speed is what we're trying to determine. All right, the distance it travels 2,500 meters. So you write that down. And it says, and time is 10 seconds. So you put that in. So speed equals distance, 2,500 meters, divided by 10 seconds. And you can calculate what that would be. It should be 250 meters per second. Number 2, a snail is moving at a speed of 5 meters per hour. Not a fast critter. How long will it take the snail to travel 15 meters? Okay, again, looking back at our formula, we know we can do it by speed equals divided by distance equals time. So speed equals 5 meters per hour. Distance is 15 meters. So we should be able to calculate 5 divided by 15 should give us our seconds. Or hours in that case. Alrighty, now what is the difference between speed and velocity? Alright, speed describes distance and time. So does velocity. Velocity adds a given direction. So velocity is a speed in a particular direction. Like I could say north, south, east, west, left, right, up, down. Those are all directions. And that would be the difference between speed and velocity.
Och 1958. Fick vi inte på världskurvan. Hittills så kommer den här mannen alltid överträffat alla förväntningar. Så att, ja, varför inte ett världsrekord? Så det är perfekta förhållanden.
The 200-meter dash is a sprint that requires tremendous amounts of athleticism. In 2009, here in Berlin, Usain Bolt broke the world record for the 200-meter with a time of 19.19 seconds. How fast was he going? Well, that depends on how you look at it. How fast Usain Bolt was going depends on if you look at his average speed or his average velocity. Speed is given by the distance over time, whereas velocity is given by the displacement over time. We'll look at each of these separately. First, let's look at his average speed. When considering Usain's average speed, we consider the entire distance he ran around the track, which is a total of 200 meters. So we get that the average speed is 200 meters over 19.19 seconds. This gives us a total of 10.422 meters per second. Now let's look at velocity. When considering Usain's average velocity, we only consider the distance between his starting and ending position, which is about 115 meters. So we get that the average velocity is 115 meters over 19.19 seconds, which only gives 5.993 meters per second. No matter how you look at it, Usain Bolt's record is still an incredible feat.
Okay. All right. Now let's talk about acceleration. Acceleration is a little bit different. And acceleration, remember we've talked about it having three different ways you can change speed. You can change the speed by starting, stopping, speeding up, or slowing down. In other words, a change in speed is one way to change acceleration. Or you can change direction. Of course, the easiest way to remember it is just to remember that acceleration is a change in velocity, because velocity already has a direction, remember. And acceleration is caused by an unbalanced force. Now, deceleration is also called negative acceleration. It just means the object is slowing down. When acceleration is calculated, again, it could be a negative number because that means it's slowing down. Alrighty, Newton's laws of motion. We did this on our digital learning day. So first, can you explain Newton's first law of motion, also referred to as the law of inertia? Alright, Newton's first law of motion is often stated as an object at rest wants to stay at rest. and an object in motion wants to stay in motion with the same speed and in exactly the same direction unless acted upon by an unbalanced force.
What's inertia? Let me clue you in. The first law from Isaac Newton says objects stay on their course unless affected by an outside force. I was rolling down the street, skateboard on my feet. That's motion, what you think? To the curb, applied force upon my board. I went soaring, hit the floor. Now I'm at rest, laying in my bed. Mama came in, put ice on my head. She says, I know what hurt you. It's a little thing called inertia. What's inertia? Well, let me clue you in. The first law from Isaac Newton says objects stay on their course unless affected by an outside force. Drop it down to the floor, that's gravity. Make it stop, that's friction. Flight is air resistance. There's a few I didn't mention. What's inertia? Let me clue you in. The first law from Isaac Newton says objects stay on their course unless affected by an outside force.
All right. How about Newton's second law of motion? Newton's second law of motion says motion is created by unbalanced forces. And mass and acceleration change in opposite ways. They are inversely proportional. So if mass goes up and the force hasn't changed, then the acceleration has to go down and vice versa. So the more mass an object has, the more force it takes to accelerate the object, so the slower it accelerates. Or conversely, the less mass an object has, the less force it takes to accelerate the object, so the faster it accelerates. All right, here's an example of it. You have a cart going down a ramp or an inclined plane there. The force of any object is the product of its mass. How much mass, remember, is mass times gravity is weight. So we just want the mass here. So you're going down and it accelerates. So it's mass times its acceleration equals how much force is actually applied. All right, here's an example of Newton's second law. You've got Mike's car. It weighs 1,000 kilograms. It ran out of gas. Okay, Mike wasn't paying attention. Mike is trying to push the car to a gas station, and he makes the car go 0.05 meters per second squared. Using Newton's second law of motion, can you compute how much force Mike is applying to the car? So the mass of the car is 1,000 kilograms. The acceleration is 0.05 meters per second squared. So we know that mass times acceleration would equal the amount of force, which would be in newtons, which is 1 kilogram per second squared. All right, so the answer would be 50 newtons, because 1,000 times 0.05 would be 1 kilogram per meters per second squared, and that is 50 newtons. All right, so here's a couple more practice problems. A 10 kilogram bowling ball would require what force to accelerate down an alley at a rate of 3 meters per second squared? Now, the first thing you do when you have a word problem is you figure out what are they asking you. All right, it wants to know what force. So I would underline that force. Okay, I'm trying to calculate force. All right, then what do I know? A 10 kilogram bowling ball. So I know the kilograms is a mass unit. So 10 kilograms is my mass. And the rate is the same as acceleration. So a mass of 3 meters per second squared. So if I know the mass and I know the acceleration, I just plug in my formula, force equals mass times acceleration. All right, Sally has a car that accelerates at 5 meters per second squared. If the car has a mass of 1,000 kilograms, how much force does the car produce? All right, first question, what is it actually asking for? He wants to know how much force. So I'm calculating the force. So I know my formula equals force equals mass times acceleration. Does it give me those figures? Okay, 5 meters per second squared. Now, I know that's an acceleration unit. So 5, and also it tells you it accelerates. So 5 meters per second squared is my acceleration. And I'm going to multiply that by the mass, which is 1,000 kilograms. So I'd write that out. So 5 times 1,000 is 5,000 newtons would be my force applied. All right, Newton's third law has, for example, it's a rocket. For every reaction, there's an equal and opposite reaction force. Actually, it's for every action, there's an equal and opposite reaction force. All right, so I have an action going this way, and the reaction is the rocket shoots off the other way. So that would be Newton's third law of motion. All right, now another example is a basketball. If you throw a basketball on the ground, it's with so much force, the floor is going to push back with an equal amount of force. The basketball goes up into the air. If you were throwing a ball down, I don't know why, I guess you're bouncing it maybe or something, dribbling it. All right, here's the concept checks that you were asked to do. Let's go over these, and you can go over them when I'm done and fix yours if you'd like for more credit. All right, so you're asked to decide which law. Answer the following questions, then state if the question is an example of Newton's first, second, or third law of motion. All right, if you walk on a log that's floating in the water, the log moves backwards. You are moving forward, but the log moves backwards. So that's clearly a case of Newton's third law. You walk forward, you're pushing the log back, and the log's pushing you forward. So you're walking forward. So it's Newton's third law. Number 2, heavier football players tend to play on the front line. Why? Well, we talked about, do you want your you want to block the other team. So you're going to put someone there that's going to take a lot of force to move. So you're going to do Newton's first law. You don't want them to move. So the heavier football players, they're more massive, more mass, they're less likely to want to change what they're already doing, which is standing still. So they will be a better block team. So that's going to be Newton's first law of motion. All right, the third one, which I think was number 4 in your paper. Sorry about that. What net force is required to accelerate a car at a rate of 2 meters per second squared if the car has a mass of 3,000 kilograms? Don't forget to include the units. All right, first, what is it asking for? It's asking for your force. All right, so force, what is force? What do you already know? You know that a rate of 2 meters per second squared, which is your acceleration. You also know the mass, which is 3,000 kilograms. So what's 3,000 times 2? Should be 6,000 newtons. Which law is this? Yes, Newton's second law of motion, F equals m times a. Alrighty, one of the last things we've done in class is force diagrams. On the force diagrams, there are very simple, like a stick diagram is of a person. They're a very simple diagram that simply shows what is the item and what direction the force is applied. The force can go either direction. It could be a push or a pull, because that's what a force is, remember. In this case, you have a block that's being pulled 2 newtons to the left and 10 newtons to the right, which means it's got a net force of 8 newtons moving to the right. So it is moving, but it's moving to the right. So both of these are correct. This one's showing all the forces on it, and this one's showing only the net force on the block. All right, if you have balance forces, both the arrows going exactly the same, the block isn't going to be changing much of anything. It's going to be doing whatever it was doing, which is probably nothing, just resting there. Okay, now another thing we've done in class, I think activity 75 had to do with motion graphs. Now, motion graphs are, you have distance and time. Distance is on the y-axis, time is on the x-axis. All right, so if you have a line, it's not changing distance because it's not going up anywhere here, but time is changing. So obviously it's not moving. It's not going anywhere, just sitting in there in park or whatever it's doing. All right, so again, this straight line going across shows you that that time is changing, but distance is not. All right, interpret the graph below. You have another one. We have distance is changing constantly as time changes. That should be showing you constant speed. It could be going either direction. All right, this one here, again, it's a straight diagonal line, tells you that it's actually heading closer back to the starting place, which was down here, but time is still changing, and it's straight line, so it tells you it's a constant velocity going back to wherever its starting point was. All right, how about this one? You've got distance pretty constant here, and then all of a sudden you start going a lot more distance in a very short amount of time. That's acceleration. All right, on this one, you'd say first, it's going at constant speed or constant velocity. Remember, the only difference is one's got a direction in it. So in this case, it's constant speed away, or constant speed away from the starting place. And then it's at rest. Maybe it's a stop sign, maybe it's parked waiting to pick someone up. I mean, who knows? And then it's again moving at a constant velocity back to its original location, but at a slower velocity. So a graph may end up looking like this. Tom starts from home. This is his distance he travels away from home. Here, the line, he's going at a pretty good clip, but then he kind of slows down. It's still at constant speed, but he's slowing down. And then this is the furthest point away from home Tom gets. And then he is going back to his home, or wherever he started out from. All right, one of the last things I wanted to talk about is identifying variables. We had a problem with this with activity 74, I believe it is. You had to actually write out procedures, and you had to identify the independent and dependent variable. Some of you really struggled with this. So let me kind of go over this again to make sure you understand. All right, there's two types of variables. The independent variable. It's the variable changed by the scientist. It's the I can control it. It's oftentimes time, like you can control how often you check it. It can be whatever you are changing in the experiment to see what happens. The dependent variable is the variable that might change because of what the scientist changes. So it is what's being measured. And again, you would always put the unit you are measuring these in. All right, so your hypothesis can tell you about your variables. If I drink Mountain Dew before bed, then I will not sleep very much because the caffeine in the Mountain Dew will keep me awake. All right, the independent variable is what you changed. You changed drinking Mountain Dew. Now, the dependent variable is what you measured, and that was keeping me awake, so that is the amount of sleep, and that would be about probably in hours. All right, another example. I'm going to give you a hypothesis and see if you can identify your variables. If I leave all the lights on all day, then my electric bill will be high because I will be using more electricity. So your independent variable would be, what are you controlling? Yes, the time the lights are on, okay? And the dependent variable, so that would be like leaving them on all the time. And then your dependent variable would be your electric bill, the actual bill, the amount of dollars that you have to spend. Again, please notice also I am writing this prediction hypothesis in the if, then, because format. Some of you did the if, then just fine, but you completely forgot the because part on yours. All right, if I brush my cat more, then there will be less fur on my furniture because more fur has been removed. All right, independent variable is the amount of time brushing the cat. So I could put amount of hours. The dependent variable, I could be measuring the amount of fur found on the furniture still. I could, take one of those brushes and clean it up and then actually figure out how much mass I have of the fur. All right, here's some tests for you. You ready? Elizabeth wanted to test if temperature affected how fast milk goes bad and curdles. She left milk in a room temperature closet, a fridge, and an oven that was turned on low heat. She then measured how rotten the milk was after 10 days. All right, the independent variable is the temperature our milk is stored. In this case, it's just a closet, a fridge, or an oven. It's not an exact temperature, but I guess you probably could get that. The dependent variable is how rotten the milk was. In other words, how much smell was there, how much it curdled, the amount of curdling. That'd be kind of hard to measure, but you could probably give it some kind of a rating scale. All right, and the last thing I wanted to kind of go over was writing scientific procedures. Some of you thought writing a scientific procedure about an experiment meant telling me to draw a data table, telling me to write a prediction, telling me to get my supplies. That is before you actually do the experiment. When someone asks you to write procedures, which are directions to conduct a lab, you actually need to tell them how to do that. So a procedure should be easy to follow. It should have step-by-step directions for conducting the experiment, not getting ready to do the experiment, but to actually conduct the experiment. Often it includes a sketch of how to set up the experiment. In our case, we just told you to go back to lab so-and-so and look at the picture in the book, and that was fine. The directions should be numbered to be sure they're done in order, the correct order. And I told many of you to check your procedures to see if you were detailed enough to have someone else read it, and then have them explain how the experiment is to be done. So sometimes you can identify just from them talking which steps need more detail because they had no clue what to be doing.